Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
I'm just going to talk about large margin generative models, which is a strange mixture of two opposite sides of the machine learning community. And he got his PhD from MIT. He was in the same class with Sumit. He worked with Alex Pentland and Tommy Yakola, and now he's a professor at Columbia University. And I'll just let him talk.
Thanks, Nebosha. All right, it's great to be back, and today I'm going to be talking about a different, more machine learning-oriented side of what we're doing. So kind of we go between computer vision and machine learning. Today I want to talk about, again, what Nebosha was saying. There's these two camps in machine learning. There's the support vector machine people that do large margin, discriminative types of classifiers and regressors. And then there's another camp, which is the generative modelers, which try to describe the phenomenon using probability distribution, which actually lets you regenerate the data. I think that there's strong complementary aspects of both of these schools of thought, and I'm going to be showing some work that we've been doing, including some of my older work during my PhD thesis, but then also some more recent work that's been ongoing in my group at Columbia. Okay, so again, there's these two communities, and I think they both have really interesting things to say about the machine learning problem, and it's nice to see them on one page, and so we can compare and contrast. There's the generative modeling people, and their tools are graphical models and probability distribution. You can describe a complicated phenomenon as a Bayesian net, or as a directed or undirected graph, and then you typically do learning again, by trying to regenerate some data that you've seen. You assume I have some IID data, and I have this initial model, and I refine the model, estimating parameters, modifying it a little bit so that it fits my observed data better. And the standard ways of doing that are with maximum likelihood, or the EM algorithm, or Bayesian inference, variational Bayes when things become intractable, or MCMC. And the nice thing about these types of models is they really flexibly describe a panorama of problems. You can put all sorts of twists on a problem, saying, okay, you've observed this variable, not this one, this is hidden, this is another task that's related, and there's all these different ways to structure the problem, including identifying dependencies, priors, insert hidden variables when you don't observe something. So it's a very rich tool for describing and giving prior knowledge about a problem. One of the main problems I find of this tool is that the objective is not related to the task. So if I really care about using this model to later do some kind of diagnostic, like predict if somebody's, let's say, tumor is benign or malignant, the objective, when I maximize likelihood, doesn't really care specifically about that type of inference, going from this variable to this one, for example. It's not really focused on that. It's just trying to regenerate the data. All variables are treated equally, and so you typically don't get the full classification performance or regression performance you can get out of this machine. Meanwhile, the discriminative approach, which is popularized by these support vector machines, says, well, let's not worry too much about structuring the problem, defining the full generative phenomenon that's creating our data. Let's just worry about building a machine that goes from inputs to outputs, or inputs to classification labels, inputs to regression outputs, etc. And you build these support vector machines. But it turns out that these are very robust, and they are able to handle, let's say, poor assumptions that you've had at the outset about your problem. And they maximize the margin on the task, which means they minimize classification error or regression error in a very conservative way, the margin, making sure that you have really an optimal classifier. They also have generalization guarantees. But again, the important thing is these don't have to be very accurate ways of generating the data, but they're more robust to this because they're being fit to this objective that really cares about the only input-output task that you really have to use your learning machine for. These try to fit all possible tasks, these focus. So these are more robust and able to sometimes get better performance. And in particular, what are those sometimes? Well, several people have published papers where they've shown better performance with discriminative techniques, including folks like Mueller with time series prediction, digit recognition, speech recognition, text classification, even things like face recognition and genomics and computational biology. A lot of the problems there, you get better performance when you throw these these systems at the task because they really optimize the classification error. So what I'd like to do is maybe try to put these on a same continuum and combine their complementary strengths. Okay? So for example, in the SCOP dataset, protein classification, you try to classify proteins into families and subfamilies and superfamilies. And there you can use these Fisher kernels on hidden Markov models to build large margin support vector machines at the very end. So you have a kernel, and then you optimize the decision boundary with that kernel. But again, that was at the time the best performing system, and currently the best performing systems are SVM based for protein classification on the SCOP dataset. So, and also shameless plug for my book, which takes some of the concepts in the thesis and I guess exposes them in a more thorough way, and also tries to build this bridge between discriminative and generative learning. And again, there's things that we've added on top of that, and actually the reason why I'm excited about this talk is we've discovered a nicer way to set up a lot of the things in the original thesis, and the book kind of brings it all together. So again, starting with the same sales pitch, generative models are natural for setting up, structuring, and providing priors in many applied learning problems. Okay, sometimes things get a little kind of black boxish when you use the support vector machines, but they have these unfocused learning algorithms that are maximum likelihood, even conditional likelihood, and Bayesian inference. A lot of times they don't really push performance perfectly towards our task. Whereas we'd like to combine these discriminative techniques, and that's what this book talks about, improving the algorithms that learn with these models, not necessarily throwing away the models, but making sure the learning algorithms really care about the input-output classification or regression problem at hand. Okay? And one thing I like to picture is a continuum, and I'll talk about that in a second. So again, a generative model can do pretty much anything, and through a generative model, you can indirectly get a classifier and a regressor. But meanwhile, a support vector machine or a standard discriminative technique is really only going to give you an input-output mapping, and you can't use it for other types of things. You can't say now I'd like to go from outputs to inputs, let's say, or now build a strange type of structure inference algorithm or something like that. It's hard to work with these beyond what you've trained them on. Generative models are very flexible. You can get any type of inference out of them, but you have to really train them the right way to get optimal performance on the inferences you care about the most. And the way you start off with a generative model, let's say that you've trained with maximum likelihood, you get a distribution. That distribution is over all your variables and the universe of variables you're going to be dealing with. And then typically you'll condition it. So you form a conditional of P of y given x, and then we'll estimate a y by turning this conditional into deterministic mapping, like, for example, picking the argmax or the expectation, and that's how we produce a label or an output y from an input x. Let's say, is a face male or female from the y hat given an image, let's say a grayscale image of the person's face. We can be a little bit more to the point and say, well, why bother with this whole big joint distribution? All we need is this. We can directly estimate just a conditional. That's what conditional maximum likelihood does. That's what logistic regression does, and so on. And then we go through this mapping. Or we could be really sparse and say, all I care about is this mapping. Well, that's all I'm going to build. And things like empirical risk minimization will just fit mapping so that you minimize risk on training data. So we can see this continuum of going from generative, where you're building the full model, to just saying, all I really need this model for. And you might have this halfway point, which is the conditional likelihood. And then also I like to structure the continuum in terms of how local is your learning algorithm to how general is it and how much generalization you can expect from it. Obviously, we can just take whatever a model is and fit it locally to just some training data that I see and put up my blinders and just say maximize likelihood only on this training data. Or I can start improving performance by imagining if there's a prior and trying to fit this data, but also with a prior kind of pulling towards more general settings. Or I can do this full model averaging technique where to generalize well, I don't just look at my data set, but I try to average models in the hopes that that's the best way to generalize to future data. Okay, we can see maximum likelihood, maximum posteriority, and Bayesian inference are the kind of continuation to the full averaging, where you get better generalization here, whereas here you're just getting the data. For the conditional versions of these things, you've got maximum conditional likelihood, conditional posteriority, and Bayesian inference. And then here I've thrown in maximum mutual information. That's what the speech recognition people do, but it's actually very similar to maximum conditional likelihood. And then for discriminative learning, where you just care about decision boundaries, empirical risk minimization just will minimize that mapping's error on your training data. But then we could be a little smarter and say, let's regularize that. Support vector machines will minimize structural risk. So it's that training data set plus some kind of penalty term that penalizes complexity. And then we can be really fancy and say, well, let's integrate over all possible discriminative models in the hopes that we'll generalize even better in the future without just looking at a training data set. And that's what these base point machines do. And that's what maximum entropy discrimination does, which is what I'm going to be using. That's the tool we're going to be using now to combine generative and discriminative. And it turns out at this level of model averaging, these things combine very nicely. Whereas at these levels, it's harder to make this combination. Okay, so that's what we're going to be using as our framework. This is joint work with Tommy Jaakkola and Marina Mela. And it starts from support vector machines. But I could have started it from generative models. We're going to come back to this kind of intersection point. So MED will subsume support vector machines. And we can start off by building a support vector machine, making changes to it, and seeing how, at the end, we can think of it as a probabilistic generative model. Okay, so let's start off with some simple data. We have inputs, x1 to xt. And we've got binary labels, a plus or minus 1 that goes with each one of these, let's say, vector inputs. And somebody says, here's our discriminant function. We want to find a good classifier that will take our inputs to their proper labels by multiplying them by this vector inner product and adding a scalar. And then the sign of this will tell us what our machine is predicting. If this is positive, this is going to predict that the corresponding y for this x is positive. The sign of this L is negative. It's the other class. So our model parameters are theta and b. That's what we need to figure out. And we were given this training data, and this is the function, the class of functions we're going to explore. So VC dimension and these generalization bounds argue that what we'd like to do is maximize margin or minimize some kind of penalty function on theta. We'd like theta's magnitude to be small, while also making sure we don't mess up on any of our training data examples. So all we say is the sign for each point in our data set of L should agree with my label, and in fact more than just agree with it, but be greater than some margin quantity. This is typically set to 1. So I want these two things to be, if this is positive, this to be positive, if this is negative, this to be negative. And that's what those constraints are saying. Typically we set the margin to 1. Minimize that norm. Okay, and that's going to say here are a bunch of positive x's and negative x's. Find the hyperplane that separates these with maximum margin, and that gives you the optimal theta star. This is pretty standard stuff. And the way we're thinking about this optimization problem is as a quadratic program, because we're trying to minimize the norm. That gives you this bowl-shaped function. We're minimizing that, trying to get closest to the minimum norm theta solution. But each one of these constraints cuts the space of thetas with a half plane, and then you keep intersecting these half planes, then you get this convex hull. And now I can just plug that into QP, and I'll get the best theta star, the maximum margin hyperplane. The problem is nothing about this is really probabilistic. We don't have a generative model. It's not as flexible. We can't suddenly introduce hidden variables now. We don't have ideas about prior, structure, etc. So we've thrown away a lot of those things. What we're going to do now is try to re-inject those things back in. Okay? So one of the complaints about this being not probabilistic is that we're finding just a single best theta star. And that might be a little narrow-minded, because there might be many other solutions that are kind of close to theta star. They're pretty good hyperplanes. They're not the single best hyperplane. And we don't want to just ignore those and just say, here's the best one. We could imagine instead giving a distribution over theta and saying, okay, here's all the really good hyperplanes. And that distribution P of theta will describe good solutions when P is high and bad solutions when P is low. Okay, so high probability on good solutions. And we can get back, by writing an answer as a probability distribution, we can actually get back the same thing as theta star by saying, oh, if that probability distribution peaks when theta equals theta star with a delta, that's exactly equivalent to saying my answer is theta star. Right? I can just say, here's a distribution, make it peak at theta star. So I haven't lost anything. But now let's try finding a distribution over answers instead of a single best answer. Okay, so how do we solve for this distribution over answers? What we'd like to do is no longer satisfy the constraints at theta star. We'd like to satisfy our classification constraints in the expected sense. So once I have a distribution over models, when I integrate all possible models, I should, on average, get the right answer. Question? Distribution over all possible hyperplanes. All hyperplanes that I could have picked, you give me a probability for each one. So all the theta vectors and scalar biases. Really, it's going to be like the posterior. We're going to find a p of theta after doing learning so that when I use it, I'm going to get a good classifier. By integrating all my decision boundaries weighted by how much the posterior wants to use them, and in the expected sense, I'm going to get the right label. This expectation right here. So if this peaked at the right answer, I would get back the exact previous framework with a single theta star. Right, I'd get exactly the same thing if this was the form of my distribution. But now I'm going to integrate over a more flexible p distribution, which I'm not really going to constrain to be just a single delta function. And I'm going to estimate that distribution.
Won't the estimation just lead to the delta function of theta?
It depends how I set up my prior. Yeah. Okay. So the next bullet is, it makes this clear. So not only do I need to find a distribution that satisfies this, because I could have picked this as well, I also want to regularize my distributions. So just like the SVM says minimize the norm of theta, I'd like to regularize this p solution as well and say I want to be as close to some prior p. So this posterior p distribution, I want to minimize the KL to some prior, and I haven't specified that yet, and also satisfy these constraints. Obviously, if I'm minimizing it and I say it has to have this form, I might be able to get back exactly what I did before, but for now I'm going to say I want to get my constraints right with this distribution when I take integrals over them, and I want to be as close as possible to the prior. Okay, so that in terms of an information geometry problem, I have this prior distribution. I'm trying to find a p as close as possible to my prior so that it satisfies these constraints. And each one of these constraints actually makes this half-plane cut in p space now. Okay, so each one of these is a half-plane. So I have this convex hull which describes solutions that will give me good classifiers, will satisfy everything. So that's this hull here, and I'm trying to find the one that's as close as possible to my prior. Okay, and that's how I'm going to solve the problem, instead of trying to minimize theta squared and satisfy the constraints with a theta star. And then when I find my distribution, this point in the space of points that does perfectly separate, let's say, the data. So now we're assuming everything's separable, and as close as possible to the prior. Then I use it by taking my discriminant function, and instead of plugging in theta star, the optimal theta star, I integrate over all models weighted by how well the posterior likes them. And that's my actual inferred output, y hat. Yeah?
How do you measure the quality of each classifier? So I understand that you have hard constraints that you have to satisfy, but how are you going to deal with margin, for example?
This is the margin we're going to try to clear the margin by 1. There is no absolute value. This is just parentheses. So the sign of the true label has to agree with the classifier you're trying to estimate when you integrate over it, minus 1. So on average, for every single classifier weighted by its probability, you're going to have 1 as you take its output and its true classification label.
T.
Yeah. We have t data points. So you want these constraints to hold for t data points. T equals 1 to capital T, let's say. So these are all a bunch of linear constraints on P over the space theta.
But there's no weighting on how well the inequality holds?
No, these are just regular inequalities, and I'll start off with just a 1 in here. The reason why you pull towards the geometrically large margin is because when you have a 1 in here and you really are estimating hyperplanes, they're kind of scale invariant. If I scale theta by 20 and I scale d by 20, I still get the same hyperplane. So setting 1 here without loss of generality will give you the largest margin.
I just have a hard time understanding where exactly is the quality of the classifier being measured.
Well, at a certain point we'll see it in the next slides when we start dealing with this margin term better. But for now you can see that if I have to clear all my labels with at least 1, then I'm not just perfectly classifying them. If it was 0, then I'm just perfectly getting everybody's classification label. When this is positive and this is positive, then I've satisfied the labeling. But if on top of that, I also want to clear kind of 1, a scalar of 1, I need to more than get the sign correct. I need to have my discriminant be actually pretty large when this is positive.
You are not distinguishing between classifiers that clear by 1 and classifiers that clear by 10.
No, just by 1 for now. Yeah.
Optimizing the normal data.
I'm not optimizing the normal data.
So all of the quality of the classifier that was coming back from was coming in terms of normalizing the norm, optimizing normal data. Now that's somehow being in your KL divergence to the prior.
Yeah. So I'm no longer optimizing the geometric margin. I'm just using a 1 in here and saying I want to at least get this kind of generalized concept of margin, how much your label agrees with your discriminant. This is a general concept of margin, not the geometric margin. I want that to be at least 1.
And do you typically use the uniform prior? So it's just the entropy of the, you're just adding the entropy to that term?
You can say that this is a uniform prior, but for now we're going to use different priors. Uniform is not always the one
If
choice.
you're using a uniform prior, it becomes basically just by a constant difference from entropy of the distribution of the data. So if you then add that back to your term up there, then it looks like free energy, but a lot likely to be defined by the margin.
Yeah. So these constraints will look like these types of likelihood terms at the end, but you're absolutely right. This is all going towards the maximum entropy setup, where you can see some of these solutions are classical P distribution. The P solution is going to be the classical maximum entropy distribution, where it's your prior times exponentiated constraints. So we can solve this, and then it makes it all clear. It's actually a textbook problem. It's the standard classical maximum entropy solution, where given my prior, the solution for P, the best P that comes as close as possible within that hull of constraints, or the one that minimizes KL subject to my classifications, is P, the posterior, is equal to the prior times an exponentiation of all your constraints for all T data points weighted by these Lagrange multipliers. And then you've got a partition function that just normalizes that distribution. This is classical result straight out of Cover and Thomas. And we still haven't specified how to pick these Lagrange multipliers, but this is the general form of distributions. Okay, so we have an analytic solution for these types of distributions that satisfy these constraints. These are inequality constraints, so these Lagrange multipliers have to stay positive. If they're equality, then they could vary, but this is textbook stuff. And then the way we pick these Lagrange multipliers is we compute the partition function that normalizes this distribution, this posterior, and that's just by integrating it over theta. And then to find the best lambdas, the ones that actually satisfy the constraints and minimize the KL, we maximize, and this is now in a dual space, the negative logarithm of the partition function, just like maximum entropy. We maximize this J lambda, which is negative log Z lambda. And here our lambda is a vector of all the possible Lagrange multipliers, 1 for each data point, and these are constrained to all greater than 0. So now it's just like the maximum entropy setup, except unlike maximum entropy theory, where typically people say my constraints are in terms of moments on my distribution, I want to find the max ent distribution that has a certain mean, a covariance greater than 3.4, and a fourth order cumulant less than 2. Instead of having those types of moment constraints, okay, where we want expectations under a distribution to satisfy some kind of polynomial, like the mean would be x, the variance would be x squared, and so on. We have these feature functions, which are the actual margin of your discriminant times the label minus the actual margin quantity. Okay, so our feature functions become our classification constraints, but it's the same now as maximum entropy theory. And unlike max ent, we don't care about the mean, the variance, etc., and we're actually solving for a distribution over models, not a distribution over our sample space X. Okay? But other than that, it's the same math.
The max ent, aren't the max ent constraints typically equality constraints instead of inequality constraints?
Exactly. So typically they are equality, but you can handle greater than or less than inequalities. You just have to lock your Lagrange multipliers to be either negative or positive, respectively, for both those two scenarios.
How can you do that?
Well, when you find the best lambda that
You
maximizes,
just make sure you don't go to solutions that obviously.
yeah,
But wouldn't that affect the maximization too? I mean,
you'd have to do something clever. So typically what happens is people will say, whatever lambdas correspond to inequalities, I have to make sure that they don't go negative in this optimization. And then you do things like Newton-Raphson, gradient descent, or iterative scaling.
But you can't use any poll method, which would try to. If you do have if you could analytically describe the surface, you might end up in a solution which would just give you bogus Lagrange values for certain other lambdas.
So when you have inequalities, you do have to make sure that this optimization doesn't drive you to either negatives or positives, depending on the actual direction of the inequality. But this is always concave. So I always get the unique global optimum with max nth. When I say max this J lambda function is always concave. So I don't have local minima issues. That's really nice here. Yeah.
So, kind of hung up on P of theta. So I see you have the constraints of defining some feasible set of thetas that respect the margin. Okay, so you want to choose a theta out of this set, or you want to define a distribution over it somehow. Is P of theta here a posterior?
It's a distribution, which I'm calling posterior kind of loosely because we're not doing, this isn't Bayes' rule. But we also have constraints on P of theta, which look very similar. These constraints are also half planes in P space now, not in theta space. So you can think of P as this continuous infinite dimensional vector, for example. Each one of these inequalities cuts that space in half. So now I'm cutting up P space with these linear inequalities. They're all linear in P. And I'm getting this, again, a convex hull, like the theta convex hull we had for an SVM. Now there's this convex hull in P space.
Are you cutting up your prior?
I'm cutting up P space, and then as I cut it up, I want to find a point in it that's as close as possible to the prior. And that's the posterior P that we're going to solve for. And the solution is the max nth solution.
Okay, so the problem is I have a feasible space of theta, minimize the KL distance between a point in that space and my product.
Yeah. You have a feasible space in P,
Which term is it?
which, well, parameterized by theta, but the idea is in the max nth language, it's a feasible set in P because of those constraints are now over P. They're not over thetas. I integrate over thetas.
I mean, if we talk about the dual, you can make it finite, right? So, for example, you can use optimization over the lambda vector.
Exactly. Yeah. So now we're optimizing over the lambda vector, and everything is actually going to get solved in the dual because P is an infinite dimensional thing. We're not going to move around in that space. It's a little too awkward to minimize continuous functions. But in the dual space, we get these Lagrange multipliers. So, okay. So we still need to specify the prior. But now let's pick some priors, okay? We had that be arbitrary. If I pick the prior to be an identity covariance Gaussian, okay, and 0 mean for the linear parameter vector. So remember my theta was really a theta vector and a B scalar that specified my hyperplane. I'm going to pick for the prior for this guy a Gaussian of 0 mean identity covariance. For the prior for this guy, also a 0 mean Gaussian, but with a sigma squared variance. Okay, a scalar. This is going to tell you how wide or narrow that Gaussian is. And same discriminant function as before, theta transpose x plus b. Now let me plug everything in and do the math that max n suggests. Here's the partition function. It's just the integral of the prior times x of all your constraints times the Lagrange multipliers. So we plug in the prior, and now we do these integrals. Following the math, it's all straightforward. We get back this expression, which now you can start seeing some quadratic terms inside the exponential and Lagrange multipliers, and we've gotten rid of all the thetas. So now this is purely an optimization over the Lagrange multipliers. Let's take the negative log of that. That's what we have to maximize for max n. Taking the negative log of that, I get this expression. And now at some point you should start recognizing this is a standard SVM equation. So if we assume a non-informative prior on the bias that says the bias can be any scalar whatsoever, I don't care. I can do that by allowing my prior with a Gaussian of 0 mean and sigma squared to be infinitely flat and wide, and that's like letting sigma squared go to infinity. Okay, so if I allow sigma squared to go to infinity, this negative infinity times something, this better be 0, otherwise I'm never going to maximize J lambda. So if sigma squared is infinity, that enforces this hard constraint that this term better be 0, otherwise you're going to get a really tiny J lambda function. So you're going to get this thing happening automatically for non-informative priors for the bias. And now plugging this in, this thing goes away, I get back exactly the SVM equation with the exact same SVM constraints, that the sum of the Lagrange multipliers times the y of t is equal to 0. And these popped out because we had inequalities in our max nth problem, not equalities. Those had to stay positive. So we went full circle. We said, let's start off with an SVM, think about solving for a probability model instead of a single optimal solution, then pick a prior. We pick a Gaussian and a Gaussian. For that choice of priors, we get back the SVM. But now we've injected probabilities, and now we can start asking questions about other distributions. Let's not just stick with Gaussians. What happens when we do this type of work with other distributions? We can start playing around. And we could also consider not just finding a distribution over thetas, but any other part of my discriminant function that I might be suspect. So maybe I don't know some values of x. Well, I can now deal with the distribution over those x's and integrate over it. I might have unlabeled y's. I could put in a y in here, and now I have a distribution over parameters and x's and y's. And I might have a non-separable problem where my margin can't just be 1. Okay? I might have a distribution over the margins as well. So now I've got this distribution. I can play around with this parametric form, and I can put more things in it and now solve and go beyond SVMs with this probabilistic machinery. Okay? So first thing we can do is we can make a non-separable SVM. And that's by saying, let's solve for a distribution not just over models, but also over margins. Okay? And it's exactly going to be the same as before. The same as the prior, normalized with your constraints exponentiated. But now I don't have to specify the margins. I specify a prior over the margins. And this is how I'm going to push the margin to be maximal. Okay, so we take an exponential prior on the margin. So for each margin quantity, my prior looks like this. It's an x which peaks at 1 and then goes negative. It has probability mass for negative margins, which means you can allow some things to be negative, but you want to go towards these big margins because it grows to the right. Okay, that's my distribution. Over all margins, it's just a bunch of independent margins for each data point. And now I plug this into the problem, and I get the partition function by integrating. Negative log of the partition function is right here. And now you'll recognize something, again, very similar to the SVM, except now instead of just having this term and this term, I've also gotten these terms to pop up, which are log minus 1 over lambda divided by c, where c is related to how quickly this exponential drops off. And this basically says lambdas can't grow beyond c, which is what the SVM folks do to regularize their problem. They clamp the lambdas, the Lagrange multipliers. That's like doing the standard relaxation of the QP program that they solve. So now we have a prior, which is a distribution over models and margins. We have these constraints on P, and we find the closest posterior in that hull. But now that gives us for free this barrier function at C, which says lambdas can't grow beyond C. Yeah.
So in general, like you have your convex hull, right? But you typically have, and so your support vectors, your support points are all coming from making that actual convex hull. And there's in general a bunch of other constraints which are way outside that. Maybe this is what you were just getting at, but the worry I would have is that since your guide goes up exponentially towards 1, there are actually things that have a margin that are greater than 1 that are out there, and I'd worry that those guys would then overwhelm the effect for everything else because they're even further out. But some of us don't have to.
It's again related to some kind of scaling property when you're dealing with discriminants, that you can scale everything. But again, yeah, so it's not really a geometric margin, but in practice we see that in some space we are pushing away from the boundary and getting to these support vectors. The framework will give back support vectors, but they won't necessarily be the geometric support vectors. The reason why you get support vectors here is many of these inequalities on the distributions are subsumed by others. So the points closer to the boundary are going to govern that distribution P. And once you satisfy those points, the others become trivial.
Well, in general, that's good because, and quite easy because you have a hard, I mean, like in the non-soft case, you have a hard constraint, and so you're forced to stay within that hull. Now that you're kind of flipping it a little bit, in that it's okay to be a little bit negative, but it's really good the more and more positive your margin is.
Yeah.
Like, then the things that have a really large margin, which are in fact irrelevant. I mean, does one end up taking and throwing away some of those in order for them not to overwhelm your problem?
Well, also this distribution is 0 for really large margins. It doesn't keep growing.
I thought it kept growing. Oh,
Yes.
I see. Okay.
You don't really
I see,
pull
I
the
see.
prior that much.
So it goes up and then flattens out.
Yeah.
I see. Okay. Never mind.
There's these priors. For instance, if you, for theta, if you chose a uniform prior, then you would lose the maximum margin completely. You use the prior that was actually contracting theta towards 0.
You wouldn't lose it completely. You wouldn't get the same solution. You would get something that would be very difficult to optimize and so on, but you would still get something that would try to find, with this, a large margin decision boundary, but wouldn't care about pulling you towards small magnitude thetas.
If you're not pulling towards small magnitude thetas, then you can arbitrarily get large margins by just increasing thetas. Right? I think.
Yeah.
If you have theta times x to be larger than a small gamma, right? Then you can just increase theta and it'll be larger than a large gamma.
But you still need to get...
theta to be as small as possible to get a really large margin classifier.
Yeah.
You get that with your prior that's Gaussian with 0 mean and unique covariance functions. But if you use a different prior, like let's say uniform, then I don't see what would be pulling it towards.
Well, you still need to get the right classification constraints with a margin. So you have to more than properly classify the data. So the effect...
Let's say the gamma p is 1. It's just 1.
You still have to get everything perfectly right.
In the past, when you set up the regular large margin problem, you were saying you're minimizing theta.
Yeah.
The reason why minimizing theta is because that maximizes the margin.
Yeah.
And in the new thing with the prior, instead of minimizing theta, you have the prior, which is minimizing theta.
Yeah.
So, but if you just use any prior that is not trying to shrink the theta, that wouldn't happen. In this case, you also have to be careful about how you set up prior on the gamma.
Yeah.
And in a generative framework, you kind of have a sense of, because you set up the structure, you know what the variables correspond to, and it's kind of obvious even to a naive person what to choose for a prior. Sometimes they'll end up in a tractable model, but...
Well, it's not always obvious to even a naive person. Even an expert, it's not always obvious.
Yeah, but I'm wondering, since you're already getting in that direction, will you end up with something that's going to be kind of more natural, why you choose certain priors? Or maybe you will lose those priors and then just some other variables that are going to make sure that you actually tend to get large margins. Because right now it really depends on your choice of the prior, whether you're going to get the large margin classifier or not.
Yeah. So I agree that you want to pick the priors intelligently. One of the things is this prior over theta is when it's a hyperplane, the Gaussian is helping you, the Gaussian over theta, pull towards large margin. But eventually, when we move away from that model, we really will be calling on the prior over the margins to pull us towards that. And we really will like this exponential. But again, yeah. And the other thing is these priors are on a similar KL scale. You know, you're computing everything in terms of KL, so you do have to make sure that the KLs are balanced. But one nice thing about distributions is you can't overwhelm one prior with another because they're both on this information theoretic measure. If I was measuring the norm of theta squared, but my margins, I was measuring them in terms of kilometers cubed, there it's very hard to specify natural metrics, whereas distributions do specify a more natural concept of distances through the KL. They're all on an equal footing. But we'll see more priors and things will change eventually as we move away from these two. Yeah.
The prior on theta, though, is not the only thing that is actually driving good margin. For example, the contribution that you get is actually linear in the margin. And this is in the exponent. So if you fix lambda sub tau for some fixed point, okay, there is actual contribution encoded in the partition function depending on how well you're clearing the constraints. But these are not really hard constraints.
Yeah.
You are taking the average of a particular theta of the margins that it has, and that goes into the exponent weighted by the lambda function. So it is not just the prior that is driving the margin.
It is.
Well, if you look at the expression for, I mean, I think this is sort of contrary to what was the expression given earlier. So, but all I'm saying is, if you look at the expression for the distribution, right, if you fix the lambda vector, the contribution is exponential in the average clearing of the margin.
Yes, but you can get better clearance by changing theta.
Well, that should be the case, right?
But if you find theta that clears by 1, then you can find a theta that clears by 2 by multiplying theta by a number.
Yes, but it's a partition function. It doesn't really matter, right? Because you have to integrate so that this thing has to work. Yeah. If you can, what I'm saying is, you are not, in order to get large margin, you are not solely relying on the quality of your prior. It is also encoded in the penalty function.
So at the end, you are optimizing distributions.
Get something from integrating.
Yeah.
Well, if you go back to the original function, if you take it to the extreme, and you don't have, and you're taking the, well, if you're taking the uniform prior, I see you're saying even if you take the uniform prior, because the entropy term was P of theta, that's going to shrink theta, so.
And in some sense, this is how he recovered SVMs, right? He said, here's the most uninformative prior, yet he did recover something minimal.
Well, it wasn't uninformative, because he was doing prior that keeps theta small. This prior was exactly theta squared, normal theta, right?
But even if I change the prior, you get a very similar solution at the end. It doesn't. You're still going to find these SVMs. You're still going to find decision boundaries. You're still going to get support vectors and sparsity. So it's partly because you're setting up this problem as this semi-Bayesian type of procedure. You start off with a prior, but instead of having likelihoods, you have these constraints. And the constraints are, my distribution, when I integrate over them, should still give me good classifiers. And you
but that's I think that's the main point in which is making, is that your objective now is still overall in terms of classification. But unless you have a prior that explicitly wants theta to be small, then you no longer have large margins or small thetas as an explicitly.
But you're still trying to get at least, so there's a scaling problem, I agree. But if you're saying I want to at least get everything properly classified with at least not just greater than or equal to 0, but greater than or equal to 1, classified with a little bit more than just perfectly getting the boundary to sneak through the data. That encourages margins, and then if there's other terms there that will encourage other types of regularization, you're also going to encourage almost the maximum geometric margin.
But it's also the entropy of the P of theta is somehow helpful. Think about that, because you have the entropy term as well. You're trying to maximize the entropy of P of theta at the same time by having the scale divergence from the prior. So even if the prior is uniform, then you're just adding the entropy to your criteria, so that might do something. But it's not as clear as in your actual prior being Gaussian.
Yeah.
Zero mean.
But in practice, we do get large margin decisions, even when we don't pick these priors so that they completely agree with the geometry that the SVMs start off with.
But the answer you're getting here, I mean, it's no longer that you're choosing a single optimal theta, though, right? You're getting a distribution over theta now. So in reality, your classifier is really an integration over many different actual theta. So even saying that you have a large margin, theta or something is not as meaningful, because in fact you could be integrating over a large space of them.
So everything is being used in the expected sense.
Yeah.
The final solution you get and the actual discriminant you'll use are all expected. So that does also inject some other types of regularization in there. Potentially also helps improve this margin problem.
Do you find the different priors that you get? Like, I'd imagine the Gaussian prior, you probably get a pretty nice peaky solution around the kind of the point that you'd expect with the SVM. But with other priors, do you see like very different amounts of fineness?
You'll get different types of behavior. Sometimes you'll get things that just move a mean around. The Gaussian is not going to change its variance. It'll just move its mean to be closer to the SVM solution. But yeah, the results will vary depending on our models, and we're going to have something from hyperplanes to HMMs to mixtures. So, there it's starting to become less and less clear exactly what the posterior is doing. But the idea is, instead of just maximizing likelihood or doing a Bayesian procedure, we start off with a prior, and we refine that prior with classification constraints instead of IID likelihood penalties, let's say, or terms. And that sets up what's a nice convex program and gives us unique optima and so on, which are fixing a lot of other computational problems with just maximizing the likelihood or trying to minimize classification error directly. So one thing we can do to go beyond now just as SVM is to start thinking about feature selection. So sometimes you might also want, with your learning machine, to pick the set of relevant features. If you have a d-dimensional space, you want to find a subset of features S that says, here features are useless for the problem, here other features are useful. And that S is going to be a binary vector with zeros and ones. When it's 0, that means it's ignoring that feature. When it's 1, it's using it. But instead of plugging this into the optimization in a brute force way, we're going to use it as part of our max nth solution and solve for a larger distribution now over models, margins, and feature selection configuration. Okay, so we want a binary vector which picks out a subset of features so that we get a largest margin classifier. This is via the discriminant function. So here's one possible setup. We take all our thetas, inner product with x, but the switch here will sometimes delete entries of some x's. Sometimes it will preserve them. So in the combinatorial optimization problem, to find the best set of features, you would try all possible subsets and see the margin that results in the SVM. And then you'd say, well, separating in this dimension gives me this margin, separating in this dimension gives me this margin. You'd actually look at the margin over radius squared. But anyway, then you end up taking this dimension, saying that's better for classification, and feature selection is trying to approximate this combinatorial problem. And there's various ways to relax it. But it turns out this is a very nice way through max and entropy to relax that problem.
And you'll use the same set of switches for each sample X.
Yeah, so everybody's going to agree on what dimensions to use for all the samples. So there's one switch and one model vectors and one bias for everybody. And the switches are binary. So now all I need to do to solve this problem is I need to define a prior. My constraints are the same form. My expected classifiers have to have greater than 1 margin, or this margin or greater than equal to 0 inequalities. For the prior, we're going to pick this switching prior, which is a Bernoulli distribution. It just puts a weight on switches being on and switches being off, right? And depending on rho, if rho is 1, then the switches are always going to be on. As rho is going to be smaller and smaller, that's more likely to have the switches being off. It's just this discrete distribution. Okay, and then we just solve the problem. We get back the same exponential form. We compute the partition function now by integrating over both theta, s, and gamma. And then we have a new partition function. And now we maximize that problem. It's also convex, or it's j lambda negative log z is concave. And here's the new optimization problem. It looks just like an SVM. When I set rho equal to 1, which means use all the features, you get 1 minus 1, that goes away, plus 1, that goes away, you get log any to e, they wipe each other out, and we get back the same quadratic term we had in the SVM before. So nothing's changed when you say do feature selection, but my prior says all the features are on. Okay? And again, this is the standard constraints we get from before. Now, if I take different rows, though, small rows, I'm going to start throwing out features. I'm going to get a slightly different optimization problem. I'll solve that. And then finally, to compute my y hat, I take the integral under my distribution, which I found through this max n technique. That's what I weight my discriminant with, and I look at the side of that. But I integrate over models and switches. Remember, it's the expected classifier. And that's going to give me, at the end, an effective linear model, actually, which we could still write as theta transpose x plus b, but now the thetas, we can call them theta twiddles, are going to have a lot of zeros in them. Okay, so for example, if I plot a bar plot of all the thetas for some classification problem that the SVM spits out, you see it likes to use all the dimensions to do its decision boundary. If I use this technique and give it a small row, you actually set a lot of the thetas to 0, the effective thetas. When you do this integral, it's basically shrinking a lot of the thetas down to 0. And for this example problem, we have this intron-exon sequence classification problem. You take these things, you form an input vector that's 240 dimensional out of these sequences, and some of them are positive class, some of them are negative. You train on 200, test on 1300, and here's the classification accuracy of an SVM with no feature selection. The minute you start using feature selection for various values of rho, you're getting about half the error right away. This is varying the C regularization parameter. So no matter how you vary the regularization, you're not going to get the right solution. You also need to explore settings of rho in addition to the setting of C to pick out good features and throw out bad features. So almost for free, we've gotten the same optimization space, Lagrange multipliers. There's one for each data point. We haven't grown the optimization problem. We have a non-linear version, non-quadratic version now. Still concave, we still find the optimal, and now we can compute the effective linear classifier, which actually turns out to be really sparse. So for free, we've been able to add something to the distribution and estimate more than just a model. Another thing we can do with the SVM is do kernel selection, not just feature selection. Again, all the stuff up until now, we were able to kernelize, because if you look at the MED solution, the only time you see an X is with an inner product. So you can just hot swap X transpose X with a kernel KX comma X. But now with feature selection, you can't really do that because you don't just see inner products. Right here, this isn't quite an inner product. But you can use this machinery to actually select convex combinations of kernels, not to do feature selection with kernels, but convex combination. And the idea is you give me D kernels for your SVM. You don't know which ones are good, which ones are bad. You want to pick a subset of them, and actually a mixture of a subset. You say, I want to use 80% of this one, 20%, 30% of this one. So just a positive convex combination of kernels to get the largest margin classifier. So it's like learning the gram matrix by taking different gram matrices and adding them up for different convex combinations. The way we can do that is by, again, turning kernels on and off with binary switches. We again pick a Bernoulli switch that looks like this for the prior. And now we have our discriminant function which says, here's our model that interacts with our Hilbert space version of the vector. So one possible mapping multiplied by the model, but pick the mappings with the switches. So we have m kernels, we have m different mappings and m different models, but then these binary switches tell you which ones you actually end up using. Okay, so there's m binary switches. You do the exact same math, do the projection now, and you get back this MED solution again, which has an analytic concave objective function. Here you see your kernels, and now you get that same log 1 plus rho business, which actually picks how to recombine the kernels. So you give me 20 kernels, I'll tell you how to recombine them to get the largest margin. So we've added kernel selection into the framework. Another thing you can do very easily is do meta-learning, where you have multiple tasks. So you want to use multiple interrelated tasks. Let's say we're doing face classification, and somebody gets a bunch of images of faces and labels them as male and female. Somebody gets a bunch of faces and labels them as adult and child. You want both those two different tasks to help each other out, and what maybe they can do is tell you something about faces in general, what's a good way to represent them. Okay, and people like Rich Corona, Sebastian Field, and so on have talked about using things like neural nets where you have multiple tasks but they share a common layer, which is the representation layer. Here what we're going to do is we're going to do this with SVMs. Typically SVMs just find a single classification model. We can use this framework to have multiple SVMs, one for different tasks. They all try to optimally say adult or child or male or female, but they all have to pick a common feature selection or common kernel selection. So they might all together, these 500 interrelated tasks all agree that you should not look at the background scenery when you're trying to recognize the face or say if it's an adult or a child. Just look at this part. So they can all help each other quickly converge their feature selection while solving their different tasks. So again, we have multiple tasks, m equals 1 to capital M, many input problems mapping to different types of outputs. And we have this discriminant function which for each different task has a different model, but they all share the same switch configurations. And now we have this type of MED constraint where we solve by integrating over a distribution over switches, n different models, n different scalars, and also margins. So we just kept adding more stuff to this distribution, and that has to satisfy these inequalities. And here's the resulting optimization function, feature selection for multiple tasks. And again, when this makes sense, this helps you. So this idea now, margin, many models, and feature selection, find the closest point subject to these constraints. If you do have a data set where you can take advantage of interrelated tasks, you can improve performance. So over here we have an SVM, and as we do more and more feature selection with an SVM, all my tasks get better when they do independent learning. But if I tell them all of you different tasks, you're interrelated, agree on one common feature selection, then you actually improve the error from all the different learners because they all have to share that one feature selection. Okay, so this is on an UCI data set. We artificially made this into a multitask learning problem by saying we have 6 classes, we'll train 6 different SVMs in a winner-takes-all setting. That's how you typically do multi-class SVMs. But here we're telling them, but don't forget, you all have to agree on the same feature selection, and that helps improve performance.
So in this case, they really are the same tasks.
Yeah, but you can view multi-class as multiple binary decisions. And we're artificially setting up a multi-class problem. This is actually the worst thing we can do it ourselves. We're shooting ourselves in the foot because each task has the same inputs. Meta-learning actually does even better if somebody's labeled some face data set, male and female, but then there's a whole bunch of different faces in another data set, which are adult and child, and so your space of X is growing. That would even further improve results.
But here, isn't it almost first point? But if the task is the same everywhere, then it certainly makes sense to tie all of your feature sets. The feature selections to all be the same because it is in fact the same task. So in some sense, it doesn't really explore that aspect of it, because if the tasks are different, in some cases you can imagine forcing yourself to choose the same features that could hurt you, whereas in this case,
sure,
it couldn't.
So when this does make sense is when there is really a feature selection that makes sense for your problem, that there are some things that are irrelevant about images, like the background, and you want to pick the features that do matter, which are foreground features. Then you would say, now let's feed these multiple faces data sets into the system. But otherwise, if they're not interrelated in the right way, this is not going to help. So it's kind of a circular argument, but it's hard to formalize interrelatedness. There's some work by Shai Van David on interrelatedness and guaranteeing generalization in Cole 2003. So now this leads us to a more interesting set of models, which is to do large margin generative models. And here we're going to get something more interesting, not because we're just going to do nonlinearities. Okay, there's something more interesting about generative models than just being able to do nonlinear things, because we could do nonlinear with kernels with SVM. And there's a limit to the types of nonlinearities you can explore with kernels, and those are kind of these deterministic mappings. But with generative models, you can do something a little more flexible. And the way we're going to build our classifiers now are to look at the ratio of 2 generative models, 1 for each class. And we're going to get this discriminant function just as the log likelihood ratio. We put a positive class model upstairs, negative class downstairs. Log of that plus a scalar bias is what we're going to say is our decision boundary. So this is exactly the decision boundary you'd get between 2 Gaussians, when one Gaussian is overwhelming the other. Well, but we could put other distributions like tree structures, Bernoullis, multinomials, exponentials, HMMs, and mixtures upstairs and downstairs. And it's actually very flexible. But the basic idea is instead of just putting a Gaussian on the positive data and a negative Gaussian on the negative data and then seeing what happens, which is the usual generative approach, we're going to wiggle the Gaussians around so that the decision boundary that emerges is large margin. Okay? And one really nice aspect of this type of learning is it stays convex. So even though this is a highly nonlinear discriminant function, it's no longer just theta transpose x, we're still going to have a convex problem because our MED constraints were expectations over the distributions. So they're linear in P, whereas a standard SVM's constraints are constraints over theta. So they're nonlinear in theta space when I make my discriminant function nonlinear. Okay, so if this isn't linear, when I start cutting up my SVM space, I'm cutting up with these non-linear half planes. And I'm not going to get a convex hull here with a convex optimization problem. I'm not going to be able to say convex program global solution. But if I'm still minimizing KL and I have these linear constraints, no matter how nonlinear this gets, this is still linear in P. I'm still able to cut the space, and P gets still a convex program. Minimize convex cost, the KL, subject to convex hull of constraints. Okay, so now we can see what this looks like. So we can actually, when can we actually solve this? It turns out the math is nice for the exponential family. It gets a little less nice for mixture models and HMMs and so on. But basically, if these P distributions are in the exponential family, so they can be written this way, as x of function of your data plus data transpose times model minus a function of your model. So basically, the data and the model only interact as an inner product, and then you exponentiate. That's exponential family. You can do all the math analytically. But you need to pick the prior that you do the projection from as the conjugate. So if this is the P here, then the prior you pick from the one that's going to be projecting onto the convex hull has to be in a conjugate form. For every single version, every single member of the family, you've got its conjugate. Just replace the K's with K twiddles. And now this is a distribution over models. And this starts off with our prior. And here's the derivation that shows that the partition function just pops out beautifully for free. Okay, we don't really have to do any integrals to get the partition function. Basically, we assume a non-informative prior on the bias. We plug in this discriminant, which is a ratio of two exponential families in here. We do the partition function integrals, which means integrate over theta plus, integrate over theta minus, integrate over the bias. And then that's the normalizer for your posterior over those three things. Here we're just looking at z theta plus instead of the whole problem. So just this integrated with log px plus right here. Plug in your prior, you plug in your exponential family term, and when you integrate them, the math is analytic, and you get back some function for the partition, which only involves the k's, the a's, the k twiddles, and the a twiddles that you had right away here. So you don't have to do any extra math. You just take your exponential family forms, you cut and paste the a k's that are standard by the definition of the exponential family and the conjugate, and that gives you your partition function. And then you start optimizing that and get your Lagrange multipliers. And it's again a convex program because this z partition function, or the j, the negative log, is going to be concave. And you can see that it's obvious because these k functions are also known to be convex for the exponential family. Yeah?
X's are all observed?
Yeah.
And this only works for regular exponential families, as opposed to curved exponential families or other things in code?
So you could have t of x here, so it doesn't have to be just... That's a regular exponential, but not curved and not hidden. But you could have definitely functions of x so that it's, you know, like a Gaussian with covariance would have a t of x there. Yeah, that's a good point. Otherwise, this integral doesn't pop out as nicely. But you could still say the true optimization, the z, if you could compute it, it still has a global optimum. It just might not be tractable to solve that integral.
So for instance, for the simplest curved exponential family is having mu and sigma tied together. So you have the Gaussian has mean mu and variance sigma or mu squared. And so I don't think that.
Okay, yeah.
So I don't think that that'll go through either.
Well, actually, I'm not sure because whenever you do this integral, right, that partition function has to be log convex.
It'll be interesting to know whether that works out.
Okay. I mean, it's okay. So the convexity is at this level, let's say, not necessarily with what we've plugged in. But again, yeah, I haven't done the integrals to guarantee that. But in most maximum entropy setups, it's very, very difficult to get this partition function or the log partition function not to be concave.
Not to be concave?
Yeah, so the j lambda is always going to be concave. Almost no matter what you pick for your priors, no matter what you pick for your moment constraints, as long as they're all linear. Because the KL is convex and you get a convex hull. The problems usually arise because the integrals become intractable or might have an exponential number of terms. Okay, so here we're showing an example where we have two Gaussians, one with a mu and a covariance, another one with a mu and its covariance. And if I did the maximum likelihood thing, where I had some X data and some O data, I said, just estimate these two Gaussians with maximum likelihood. I'd find the mean of the X's, find the covariance of the X's, and I give you this Gaussian. Find the mean of the O's and the covariance of the O's, that gives me this. The decision boundary is right down the middle, and it's on a very good one, right? But if I tell you instead, I want to maximize margin, and I solve for the MED solution using the previous slide, you're actually going to shrink this Gaussian out this way, stretch this one out this way. They're not fitting the data as nicely, but then the decision boundary they get is optimal. Okay? And here you can see what's happening in terms of the Gaussians. When I first set them off at their maximum likelihood configuration, I'm getting this. And then what's happening is the decision boundary, this Gaussian is peaking up, the other one's getting wider. And then you can get this perfect quadratic, because that's within the range of what these things can do, these ratios can do. Yeah.
Well, this example raises an interesting question, because, on the one hand, it's a great example of your technique, but in some sense, what you end up at the end is not at all a generative model of the data, other than the fact that, it generates something, but it's not a generative model of the marginals. So the question is it, it seems like, and there are kernels you can use that are quite flexible in terms of boundaries, whereas, so Gaussians are limited to quadratics and so forth. Is this really something more than just saying, having a different kind of kernel, or having a different kind of parameterization of boundaries?
So that's a very good question. There is something different about this technique over, let's say, just picking the right kernel. One of the issues, so sometimes there's something about the generative model that is valuable, sometimes there's something that's completely spurious. So one of the things that, okay, so we know these things are good for specifying clumps that are ellipsoidal or whatever it is and look like these bumps over here. We might be off about the statistics and maybe it's a heavier tail distribution, but it's still a bump or something like that. Another really natural thing about these Gaussians is they're affine invariant, right? So I can remove my data off by a kilometer to the northeast or something, we would still find the same decision boundary. I could have mimicked exactly what happened here with a polynomial kernel and taken all my x's and added on x squared and then solved the SVM, but that's not translationally invariant. So by using this generative model, I know as a generative model, when I know what my data does generatively, I can talk about affine invariance very naturally at this level. And this does give you affine invariance. So we actually end up projecting from the prior, which we picked as the maximum likelihood prior, actually. This is the original kind of Bayesian solution. We projected to find the largest margin classifier that results from it. Okay, but again, this type of setup, affine invariant and Gaussians are known to be able to do anything with rescaling the axes and moving the means around. So there's this natural thing that comes out of the generative approach that doesn't come out with a discriminative one. Maybe you could set up affine invariance discriminatively, but again, you have to re-engineer your learning architecture. Here it involves picking the right models. Here are some performances, again, on standard UCI data sets. The important thing is, on testing, the same model with maximum likelihood doesn't do very well, but it gets half the test error with the maximum entropy discrimination Gaussian. And it starts to perform similarly to the SVMs, potentially better because, again, sometimes some things aren't very well handled by kernels. And similarly, on this other data set, again, you get very good test error with the maximum entropy Gaussians, much better than the maximum likelihood Gaussians because you tell it, I care about going from this input to that output. Not all data is treated the same way when we've finally built our learning machines. So we shouldn't just try to regenerate it all. Some parts of the distribution are going to go and are going to be used to estimate other parts. So we should integrate over the hiddens and go from input to output where we form these distributions, not just say form a distribution of everything. And again, you can start mimicking results of discriminative techniques by using generative models. Hopefully improving them when you know something about the problem. Here's a little animation of the Gaussian that we saw earlier. I don't know if I can click on it. So starting off the maximum likelihood for the prior, we do the projection. And again, if we were to optimize this thing for minimum classification error, I think I might restart here. So it showed you how to move the two Gaussians. We would quickly get stuck in a local minimum because you could see classification error can go to 0. Classification performance can go to really bad, So this is a really bad decision boundary. we'd never get to this if we were trying to minimize classification error in a greedy gradient descent way. Okay? Here we're getting it because it's done in a convex space. We have a convex program. We know we're going to end up at a unique solution. Just like the SVM improves over the perceptron by not aggressively trying to minimize classification error, but sets it up as a convex program. Here we're similarly improving over minimum classification error with generative models by setting it up as a convex program. So now here's the hidden variable scenario. When we are no longer in the exponential family, we have something which doesn't have an analytic solution for the partition function. We instead have these mixtures, for example, where you have log of a mixture of Gaussians over log of another mixture of Gaussians, plus some scalar bias. So let's take a look at a scenario where this happens, and where maximum likelihood can be really, really bad. And this might look like an artificial scenario, but we can imagine this could happen in practice. And I'll show an example of how this could happen in practice. We've got red dots here and here, and blue dots here and here, red dots here and here, and blue dots here and here. And I give you 2 Gaussians for each class. And you can't change their covariances, you can just slide their means around. So if we take my red Gaussians and slide them around, and my blue Gaussians and slide them around. Okay, if I were to go off and say, now do maximum likelihood, I would do something like an EM algorithm. I'd give you, the maximum likelihood solution is actually this. You take the blue data, send it off to the blue Gaussians, fit them with EM, red data goes to the red Gaussians, fit them with EM, come back and drop them in, and then the decision value you get is basically everything above 4 is red, everything below 4 is blue, and that's 50% classification error. So you haven't learned anything in terms of a classifier. This is the maximum likelihood solution for this, and this is the log likelihood for this generative model. But if I instead took the models and set them up this way, so red, blue, this is the best discriminative model. This minimizes classification error. It has a very bad log likelihood because it's not even on the data. The models aren't on the data. But this is going to cut it up into red, blue, and get almost perfect classification. So now you might say, well, you know, Tony, again, this is a really horrible generative model. It's not on the data. And I'd say, I agree. And you might say this is artificial. You really should have used 8 Gaussians. I also agree. But let's say you got some real knowledge about the problem domain that some biologist told you. Really what's happening is this phenomenon is, you know, it's 2 classes, both of which are bimodal and they're interlaced, right? And this is a real dimension that matters, the y dimension. X is just some other measurement he's given you in his data set, which he should have never given you. Okay, so he was right about the generative model coming from 2 red Gaussians and 2 blue Gaussians if we just project this data on 1D. He was absolutely right about that. His intuition was correct. But for some reason, there was some other variable he stacked onto his data set, which was just oscillating with Gaussian noise between 20 and 0. Maybe this was one of the students was using the data chip, and he mistyped some calibration. On another day, on Tuesdays, another student typed in the calibration. So you're getting this artificial extra dimension, but the generative model is actually really good if you look at the right dimension. So this is when this can happen, when you have the right generative model, but because of some other problem with robustness, heavy-tailedness, or some other data coming in, or some rotation of your space, something got a little bit broken, you want to fix that brokenness with the discrimination. Okay?
For example, all biologists, first thing they do, they look at every dimension. Everything in Thailand, see what that follows. So they would drop the other dimension probably in this case.
I see. Yes.
For biologists, they're very frequent.
Okay.
They would miss that dimension.
So I need to use some other
science paper on how that dimension doesn't work.
I see. So this would be a paper for, so maybe I should use doctors instead of biologists because they have to run to the operating room and they don't have time to delete that dimension or something. Okay. So that's poor for maximum likelihood, but discrimination can help. But one of the problems when you deal with mixtures is the partition function is non-analytic. You can't use the previous slide to just solve the integrals. And you can kind of see why, because at the end you're going to get this partition function which involves products over all your data of these sums. If you were to compute that partition function exactly, you would have, you know, let's say 2 Gaussians taken to the power of t for t data points. That's the number of terms you'd have to solve in the integrals. So this gets really ugly, just like the maximum likelihood with hidden data. You need something like EM here, but it turns out we don't do EM. What we instead do is we solve all these different constraints by doing iterative projection. Okay, so we have T equals 1 to capital T intractable constraints on the distribution for each one of your points. For each one of your points, the positive mixture has to beat the negative mixture, okay, by integrating over all the models. Turns out to solve this and find the closest point to the prior to the green hull of constraints is intractable because that partition function has order m to the power of capital T terms, where m is the number of mixture variables you have. So what we're going to do instead is we're going to pick a point randomly in here, find a smaller, more restrictive convex hull, the purple hull, and find the closest point to the purple hull. And that gives us a point here. And then find another hull which is centered around our most recent projection and find the closest point to that. That's here. Then center the convex hull around that most recent projection. So you're going to keep projecting and you're slowly going to minimize the KL instead of doing it in one shot, because one shot is too much computationally. So we're going to do smaller, more restrictive convex hulls, but they're actually going to be simpler because they're not going to have this intractable partition function. Okay, and the way we're going to do that is we're going to say lower bound the top term, the model that has to win, the positive has to win on positive data, the negative has to win on the negative data. Lower bound the term that has to win with Jensen's inequality at a current distribution, at a current posterior over hidden variables, and it has to beat the incorrect class for every setting of the hidden variable of the incorrect class. So lower bound on the positive mixture has to beat every single Gaussian by itself for the negative mixture. The winner, lower bounded, has to beat every single setting of the loser. Okay? And that gives you a more restrictive setting, but it turns out now we have not just one constraint, we have n constraints, because the lower bound has to beat every single Gaussian by itself. So instead of 1 point constraint, we have maybe for 10 Gaussians, 10 constraints. I have to beat every single one of these negative guys. So I can rewrite the constraints this way. Here's this distribution over hidden variables. So my bounded mixture of Gaussians is over here. I get the sum over variables of log p's. The entropy term is in there, and then we have to beat each Gaussian by itself for n equals 1 to capital N. On the positive data, the positive guy has to beat every single negative. And for the negative data, the negative guy, with his Jensen bound, has to beat every single positive. Okay, so this is a little bit more restrictive. This is kind of like the argmax type of hidden variable treatment, right? With k-means. K-means is like this. It's a winner-take-all, but it's a winner-take-all on the negative class. And so we get the smaller hull and we do projections. But notice here, there's no more log sums. And all these integrals actually can be solved in closed form using the trick on the exponential family page. No more log sums, and all these things can now be done, but now we've gotten more constraints, right? For every positive example and n hidden variables, we've got nt plus mp negatives. That's almost multiply our number of constraints by, let's say, our number of hidden variables.
Should be in a pretty bad shape if your hidden variables were continuous.
You'd be very bad shape if your hidden variables were continuous, or if you had really large numbers of hidden variables like in HMM, where you've got an exponential number of hidden variable configurations. But I wouldn't be up here selling you the sales pitch if I didn't have a solution to it. But yeah, so the idea now is we iteratively do these projections. We compute the best possible hidden variable posteriors, which center the convex hull around our previous projection, by taking the expected log probability models with our current distributions. So this is like EM, except your E steps aren't at theta stars, they're integrals over the P theta. That gives you this distribution over hidden variables. And then now you solve this MED tractable projection, but it's got more constraints. N times T and N times T. So you've multiplied things by, on average N. But these are solvable very easily. And then you just iterate this over and over again. And for the case of a mixture of Gaussians where we're only estimating the means, if we use non-informative priors, so just like the B being non-informative, etc., step 2 can be written exactly as a quadratic program with a total of NTP plus MTP constraints, because they're all, and Lagrange multipliers. They all have to be positive, and there's that many variables to solve, and they sum to 0 the way that SVM sum to 0. But now I can do this and then iterate it with an E step. So I do EM and SVM, or EM and QP, and I maximize the margin of my mixture of Gaussians. it's a little slower now because, again, QP is order T cubed, but now becomes TM cubed because there's 2 Gaussians or M Gaussians. And so it is pretty slow. Here we have this toy problem we're showing, and this is the actual convergence we get. We get a large margin decision boundary. We've estimated a mixture of a total of 4 Gaussians in these kind of competing mixture models. And it's fairly slow because we have to replicate all the constraints. But you could do this with SMO instead of quadratic programming. So one of my students, Darren Lewis, is implementing this in SMO, so we can do bigger data sets. But for toy data sets, this seems to always converge to this optimum. So empirically, this is pretty global. Whereas if you took the mixture models and you tried to maximize them with gradient descent and classification error, I don't know if you've ever tried that, but they always get stuck and they do really bad jobs. Here we always get this solution every time we've run this code. Except it's slow because of this QP setup that we've multiplied the number of points. And the reason why they're all here is because we started off the prior, just like the SVMs, 0 mean identity covariance for the parameters. Had we started off the prior at the maximum likelihood solution, my guess is we might have these points closer to the data. Because that's trying to say, bring the model as close as possible to maximum likelihood, but still satisfy the classification constraints with large margin. Okay, so now, so for people who are worried, again, the problem with this scheme, when you say the winner, its Jensen bound has to beat every single setting of the negative class. Well, if the negative class is something big, like an HMM, it's not just capital N equals 2 or 3. You have to beat the other HMM for every single state path in the negative HMM. So the bounded positive winner HMM has to beat the other guy for every single state trellis. So in a graphical model, that number is huge. For an HMM, it's number of states to the length of the sequence, to the power. So if you have an M state HMM and it's T steps long, that's M to the power of T, winner against all possible losers, that's a huge number of Lagrange multipliers. So forget about putting that into QP. But if you actually write out the Lagrange multipliers as, you know, as a problem, and you actually do the solution for MED, we see that it actually simplifies, and we end up minimizing these really factorized Lagrange multipliers, where the Lagrange multipliers actually start to behave like posteriors over hidden variables. Okay, and this is a little like the Taskar and Kohler work, and before it, I guess Altun and Thomas Hoffman papers, where instead of your Lagrange multipliers just being a function of the variable, and so this Lagrange multiplier is for the ith data point, and you have to beat Gaussian m equals 1 and Gaussian m equals 2. Now you have to beat every single state trellis path of the losing HMM. So the Lagrange multiplier is over all possible state paths. It looks like this big beast of a Lagrange multiplier vector. You've got many of these, but it turns out when you do this technique and you do the integrals, these Lagrange multipliers inherit the factorization of the hidden variables. Okay? And what we end up getting is, due to the factorization of Q and Q bar, those are the hidden variables from the E step, we don't have to deal with every single winner and loser configuration. We can just say, solve for these pairwise Lagrange multipliers that when multiplied out form the actual original Lagrange multiplier. So they literally act like the posterior distribution for an HMM, which is a bunch of pairwise cliques multiplying to give you the probability for the full state path. So now we have an optimization problem over these pairwise tables. There's capital T of them for a T-length HMM. And they also satisfy constraints just like the distributions, that if I marginalize out over one variable, I get the Lagrange multiplier over the remaining variable. So they literally act like distributions. It's just that they're not normalized to 1. They're normalized to some other quantity between 0 and C. Okay? And I actually asked physicists about this, and they say in many physics problems, when you have these types of constraints, the Lagrange multipliers will actually be distributions, and they're very used to thinking of Lagrange multipliers as distributions. It depends on the types of constraints, of course. Typically, there's this duality. If you're enforcing a constraint that, you know, something's got to have a mass of 4 kilograms, the units for the Lagrange multiplier are in inverse kilograms and so on. But in many physics problems, you're going to get these Lagrange multipliers being distributions. And here we have the nice setup that they have to behave like posteriors, scale posteriors that factorize according to Bayes net. and then we can plug this in and solve for these small tables, and for the m-state HMM case, on a sequence of length t, your quadratic program is not over n to the power of t possible constraints, it's tm squared. So you take number of sequences, multiply by the length of your sequences, multiply by number of states squared. So it's still pretty big, but it's not attractively big, and now we can handle graphical models in general where you inherit the factorization of your hidden variables. Okay, and we're just implementing this now. My student Dan Lewis is writing this up. I just want to flash the quadratic program that you end up solving for the HMM. So this is it, and we have QP of this. We're still debugging it, but hopefully we'll have some results soon. But it's a tractable number of Lagrange multipliers. And you see all these pairwise tables. That's basically what we wanted to see when we did the math. It all depends on pairwise cliques, and the Lagrange multipliers look like pairwise cliques.
How is it related to CRF?
It's very closely related to CRFs, or actually more closely related to Taskar and Kohler's paper, where they didn't have hidden variables. They had labels that were interdependent. And then you have to minimize this quadratic program over pairwise cliques and so forth. Here we don't have the labels. We have a hidden variable problem, but we know how to solve it by doing these iterative projections, where we basically get these expectations that look a lot like EM steps. We do an E step and a kind of Taskar-Kohler step. But again, this was derived completely independently. We didn't have to make assumptions about how the problem is structured. These constraints fall out of MED, the maximum entropy discrimination. The max ent tells you the maximum entropy solution is the one where the Lagrange multiplier is factorized this way. We didn't have to make any specific assumptions or things like that. I know the Taskar and Kohler paper, they have to assume that margin grows, I think, in a different way than the usual SVM margin growth. But again, I don't want to say that there's something different about the derivation. The point is this falls out of the maximum entropy solution. And, you know, so that it's a very nice general way to solve discrimination with generative models. That's what we're trying to really say, because you can do all sorts of things with it, and all sorts of efficiencies pop out, including things like getting SVMs back, but doing feature selection, which is otherwise really difficult combinatorially. Kernel selection is also difficult combinatorially. Meta learning. And then exponential families come out nicely as convex programs. And then we can do these hidden variable problems, which again might have combinatorics, but the convex program with MED, again, does the right relaxation, and we get something efficient. And at the very end, I mean, the main theme is we're not doing maximum likelihood. We've put in the data through constraints on the data. You have a prior, and you have constraints from your data, and that leads to a nice convex problem, just like the SVM, sort of minimizing some penalties or classification errors, puts in the classification as constraints, and then solves some regularized large margin thing. Again, I think it really helps to think of the convex programming aspect of the problem that limit number of local minima and keep it efficient whenever possible. In dual space, all the stuff is efficient. In primal, it's extremely inefficient. So just my collaborators, Darren Lewis, one of my PhDs, Tommy Yakala, Marina Layla, and Bill Noble, and some links to papers, and of course these are all on my homepage. Thanks. And the book, too.
Feature selection is kind of funny because you don't really throw out features, right? So in some sense, it's not what people typically call feature selection. And then you also have this funny delta parameter too. So what do you do? How can you choose this delta parameter? And
so you mean the row parameter, not the delta parameter? Yeah. Sure.
The row parameter.
Well, again, the most simple thing to interpret rho as is rho is a function of the total number of features you're going to keep around. So I could have specified I want to keep 23 features, and that corresponds to the setting of rho. If I were to threshold at some really... So again, this isn't feature selection. What we end up doing is we threshold really tiny weights, and it almost gives back the exact same performance and classifier. We get these almost vanishingly small weights.
Rho is not around the hat. If rho is around the hat, then you can't really throw any features away. So it seems like it's only feature selection if you have a really small row.
Typically, rows we have to have small rows, otherwise you're not really throwing out any features. But this technique, I agree, would not work if you wanted to keep around most of your features and just throw away the worst 10 or something out of 100. Then it's not clear that you're really thresholding a bunch of really tiny weights. But we do get reasonable performance. Most of the time we get these tiny weights we can just throw away. And most of the time we see as we decrease row, we're getting fewer and fewer features left around until we get down to one feature. So there is this relationship, but it's not completely deterministic. We haven't completely characterized the mapping from row to number of features either. I think there's some work to be done there, but you could say it's somehow monotonically related.
But as row becomes really small, your performance is going to suffer. It's supposed to be better as some of the graphs, right?
Exactly. Some of the graphs, when you have row on a log scale, when you get to 1 e to the -7 or something, you're picking away too many features. And you're down to 3 features when you need at least 20 to do any kind of discrimination. Yeah.
Are you saying it is monotonic, or like do you have measurization as you decrease row or not?
Well, empirically we've seen that as you reduce row, the number of features gets smaller and smaller until you're down to about 1 feature.
Yeah, sure, but they go down consistently. That's what I'm asking.
More or less, but this was just an empirical result, so I'm not going to say for your problem it'll do that. But most of the problems I've worked with, the number of features you keep around does go down as you decrease row.
So I guess Chris's question is that this point is that you can't pick row. You don't know a priori what row to pick.
You can't pick row, you need some other criterion, or you could do some hyperparameter business where you
Pick a very small row, you'll have a very bad solution. Pick a row equal to 1/2, it'll be the same as if you didn't have any feature selection. And then the only way to pick row, I guess, would be some sort of cross-validation. I don't know how that's in training.
So I agree that row we're picking with cross-validation now. We still don't have that many parameters that cross-validation is too nasty, but I agree that one way to do it would be to introduce a hyperparameter, a distribution over rows, and cascade the problem the way the Bayesians typically do. Yeah. Yeah.
You do that in the MED question.
You can have hyperparameters. Yeah.
You didn't have any examples of that, did you?
No, I didn't, but you can still solve these integrals, and you can see sometimes that the switches and so on, when they're cascaded, all you're doing is you're modifying the integral from the previous one. So once we've solved for that integral, if I have another hyperparameter, I can still integrate whatever z partition is left now with the remaining parameters. So I could also integrate over the row inside the partition function, right? I mean, we can see what it looks like. It might be fairly nasty, but if I didn't pick a specific row, but had let me go back a little bit longer. Okay, so imagine there's still an x in here, and this is z. To get the partition function for one, I'd also integrate over the row hyperparameters. I'd multiply x of this with my prior over rows, and then integrate out, and hopefully this row will vanish analytically, and I'll get a different expression, which is like a hyperparameter over row.
Yeah, the question is, do you have any examples of where the hyperparameters disappear nicely? Because usually they don't. I mean, that's the problem in Bayesian analysis. There's a handful of places where they disappear nicely,
Yeah.
and they're rare, and they have special names. So,
Sure.
So I'm just curious. That's why I was surprised that you said that. Oh yeah, you can just throw it in there. So yeah, you can mathematically, but can you do it tractably? And you don't have a.
I haven't actually solved any hyperparameter problems in closed form by hand, but I think there might be some that are solvable, like you're saying, and some that are really impractical. And
I would just be I wonder whether or not a beta prior would work out nicely or something like that, because it's the conjugate of that,
But I mean,
it's not probably doesn't have the right form. So,
but visually, you've got this x of a sum of log rows, so you'd have to be really careful how you pick that prior, or if there is one that will integrate that nicely. But it's a 1D integral again, so there might be other things to try to get this partition function. Again, you need to optimize this partition function. You don't need to compute it exactly, so that might also be helpful.
So, I have one more question. The last part of the talk, you're still doing the binary classification problem more or less, and even though you can have complex it's sort of like looking at the graphical model that has one parent variable that's very simple, say either the left or right, and you can have arbitrarily complex models in left and right. But you're still not optimizing inference over all hidden variables in the model. For instance, you're not, when you're doing your HMN, separating figuring out which HMN applies to the model between the two. You're not making sure that your posterior, you have a high quality posterior that states of that HMN, only which HMN to use of the two. So in that sense, actually the previous topic, which was multiple SVMs that are doing multiple problems, but forced to share some features, that might actually be a framework that's more flexible, easier to develop in something that looks more like the generative model, graphical model paradigm that has multiple variables, and you can now treat them all the same way, meaning you want to be certain about your posterior, because your goal is posterior, right, rather than the likelihood of the data. So what do you think? How can you actually extend this to really be a framework that doesn't only like the data, but rather always gives you whatever question you ask about any within variables, it's optimal, or on average it's optimal of all within variables? Or would you in that case end up with just the same thing as an maximum likelihood model?
So I think that's a good idea, what you're suggesting, that it's not just a binary classification. We're moving towards that. Now we're looking at this is a way to do generalization with constraints. And you integrate over these models, but they don't have to be classification constraints. I could say, here's a whole bunch of constraints of the types of things I want to do with my classifier down the road, and it might be that this hidden variable is higher than this hidden variable. You'd introduce that as another constraint. So you'd solve for your posterior distributions, you're going to reuse on future data, but it's not really just classifiers, not really just regressors. Any kind of constraints on that distribution you could set up and say, well, I want this hidden variable to always spit out a higher likelihood or probability value than this hidden variable setting. And if you show it all the constraints you cared about in your training data, and you set up this problem with MED and did this projection, hopefully you generalize nicely. And there are some results in PAC-Vs that we're starting to explore now, which show generalization guarantees on classifiers and binary classifiers, but you can actually apply these generalization guarantees to any types of constraints on maximum entropy solutions. So if my max and solution satisfies these 14 constraints, nothing to do with classification. On my training data, it should satisfy my classification constraints on future data with the following generalization guarantee, sometimes possibly a loose one, I agree, but you can get learning theory generalization guarantees on arbitrary constraints from PAC-Bs. And we're starting to think of the problem this way, not as a classification, but find a distribution, but I need that distribution that satisfies specific constraints, not just to fit through some likelihood criterion.
That's nice, but it's separate from what I'm thinking about. And that's just if you have a graphical model or a model with many variables, and if you're saying instead of modeling the likelihood of the observed data to be maximized, I want to always be right in terms of my inference. And since your model is crappy, you cannot always be right. And if you're right on one variable, maybe you're not right on the other variable. That's also possible, where it's kind of counterintuitive to the way we think about generative models. So my question is, can you somehow optimize this, being right in terms of posterior on every model, sort of like you're always right in terms of posterior in your mixture of Gaussian model, with the first magnitude that you provide. And if you formulate it like this, does it just degenerate back to the maximum likelihood because on average on over all the variables you have to be right, or is it actually a completely different thing? Yeah, that really is giving you better inference over time on all variables, not just one thing that you choose.
So that's a good point. I would hope that it's not going to degenerate into maximum likelihood, primarily because you're solving these constraints, these inequalities that are going to be convex programs. There's no way that you're going to get something that just, I mean, maximum likelihood and likelihood-based versions of this, you don't end up reweighting data and ignoring data and some constraints subsuming others. So you still have to solve some kind of quadratic program at the end, which says these constraints matter, these don't. And even if you say here are all the constraints, well, some of them are subsumed by others, some of them might be more important than others in the way you set up the problem. So
be the same as much likely because your simple model with just one variable, mixture model, is not the same. So it's not always the same. But I'm wondering if there's many variables, do you lose this advantage that you have or not?
So, yeah, I mean that's still an open question. If you try to satisfy too many constraints, you start giving up. And I think it's a trade-off. You have a limited number of resources with this generative model. You need it to do certain things for you. If you really needed to regenerate the data in terms of a compression type of argument or something, then the best thing to do is to do the Bayesian or maximum likelihood estimate. If you really needed to do certain types of inferences where some quantities have higher probabilities than other quantities or some inferences, then you need to do this constraint type of framework. And this could also hold for classification and regression. We've shown regression problems this way as well. But at the end, yeah, you're saying what are you going to use this model for? You have limited resources. You can't do everything with it. You should set up the trade-offs. We're arguing for trade-offs in terms of constraints and inequalities, particularly on classification, which is what most people use this stuff for.